Um, okay, so the title of the course is Gaussian measures, and today we have a lecture one. I called it Generalized Wiener functionals and capacities, but basically I will speak about properties of Gaussian measures. And in general, I split this course into two parts. So the first one will be devoted to Gaussian measures, and the main task will be to define what is a capacity for Gaussian measures and how it is related to generalized Wiener functionals. And the second part will be devoted to the notion of finite absolute continuity, which is in a sense a generalization of the corresponding theory for the Gaussian measures, in particular of the Ito-Wiener expansion for Gaussian measures. Okay, now, let me tell a few words about Gaussian processes and measures. A Gaussian process is a family of random variables defined on some probability space, such that the joint distribution of any finite number of these random variables is a Gaussian. It means that its characteristic function has a form. So if we take the characteristic function of the linear combination of x tj with coefficients lambda j, then this characteristic function equals exponent ia lambda minus 1/2 a capital lambda lambda. Here a small is a vector is an n-dimensional vector, and a capital is a symmetric non-negative definite matrix. And in this case, actually, a small is a vector of expectations, and a capital is the covariance matrix. Gaussian processes are, in a sense, like one of the most convenient objects to study in the theory of stochastic processes, because many characteristics of a Gaussian process, they either can be found explicitly or they can be described in a relatively simple way. Also, Gaussian processes naturally arise as limiting objects for more complicated models. So one can recall the central limit theorem when we get a Gaussian vector in the limit in distribution, or more complicated the Donski's invariance principle. Brownian motion, which is a Gaussian process, is a basic object to define stochastic differential equations. And again, many branches of theory of stochastic processes that are under active research, they are based on the theory of Gaussian processes. A Gaussian measure is the distribution of a Gaussian process in some space. And the study of Gaussian measure allows to use tools of functional analysis to study stochastic processes. So what we will do now, we will actually define what is a Gaussian measure, and look at some properties of these measures. So we will have the following framework. So X will be a separable Banach space equipped with the Borel sigma field B. X star will be the dual space of X. So this is the space of all linear continuous functionals on X. Then a probability measure on X is called the Gaussian if the Fourier transform of this measure has the following form. Okay, here must be L. So the integral of exponent IL of X, which is called the Fourier transform of gamma, equals to the exponent IL of A minus 1/2 L of RL. So here A is a vector in X, and R is a linear continuous mapping from the dual space into X. So A is the analog of the expectation, yes, and R is the analog of the covariance operator. Okay. And equivalent definition that every linear continuous functional has a Gaussian distribution with respect to gamma. Let's have a look at some examples. If we consider a probability measure on the n-dimensional Euclidean space, then it is a Gaussian measure if it has the following Fourier transform. So gamma of lambda equals to exponent here I, the inner product A lambda. A is a vector in Rn, and minus 1/2 the quadratic form of some symmetric non-negative definite matrix. Well, and again, A is like is the mean value, and A capital is the covariance matrix. If n is equal to 1, mean is equal to 0, and the variance is equal to 1, we will denote the measure by gamma 1, and this is the one-dimensional standard Gaussian measure. Another example, consider a standard Brownian motion, one-dimensional. It is known that it has a continuous modification, so we can consider the distribution of the Brownian motion in the space of continuous functions. This means that the distribution of a Brownian motion, it is a measure on the space of continuous functions that can be defined as follows. The measure of a set A, now A is some set of continuous functions, yes? So this is the probability that the realization of a Brownian motion belongs to A. Okay, so since Brownian motion is a Gaussian process, the measure gamma W is also a Gaussian measure. Okay, let's recall that the expectation of W is 0. So we have A is equal to 0. And also recall that the expectation of WT, WS is equal to the minimum of T and S. And this allows to find the covariance operator R for W. Now R acts from the dual space. Okay, and the dual space to the space of continuous functions is the space of signed measures on 0, 1. Okay, if we have a signed measure mu, then okay, let's do it like this. The action of mu on RW mu, it is the variance of the action of mu on W, which is the variance of the integral of WT mu dt. And this is equal to the double integral of the expectation of WT WS, which is T minimum S, mu ds, mu dt. And here we find what is the action of the covariance operator on mu. Okay. And one more example. Consider the Hilbert space L2. Yes, this is the space of sequences n such that the sum of xn squared is finite. Okay, now let's also consider independent standard Gaussian random variables psi n and a sequence of coefficients lambda n such that the sum of lambda n squared is finite. Also, let En be the canonical orthonormal basis in L2. Then the series lambda n psi n En is almost surely convergent in L2 because if we take the sum of lambda n squared psi n squared, yes, the sum of coefficients squared, and take the expectation. Okay, so since psi n are independent standard Gaussians, expectation of the squared is equal to 1, so we have the sum of lambda n squared, which is finite. This random element in L2 makes sense, and its distribution is a Gaussian measure with the is there any questions? Maybe not. Okay, so the covariance operator of this measure has the following form. Okay, let's maybe check this. So if we take the product of H and RH, it is the variance of H and sum. Which is the variance of the sum lambda n, H E n psi n, and this is equal to the sum of lambda n squared H E n squared and this sum is actually the product of vector H with this element. Um, so not to over complicate things, in what follows, we will assume that A is equal to 0, A small. And now we introduce some important objects related to the Gaussian measures. So first, X star gamma, I will denote by X star gamma the closure of the dual space in L2. Okay, so this is all limits in L2 gamma of linear continuous functionals on X. Okay, and for each function f from this space, we can also define the action of the covariance operator on f. So Rf, it is the integral of x-valued function f of x times x. This is the so-called Bochner integral, and well, I will not go like into this theory, but the main property of this integral is that the action of a functional L on this integral, it is the integral of f of x L of x gamma dx. So it's like we act by L on the expression under the integral. And the next object is the Cameron-Martin space of the measure gamma. So let's define the norm of a vector H as follows. Norm of H is equal to the supremum of L of H, where L is a linear continuous functional, such that its variance under measure gamma is less or equal to 1. Okay, let me recall one more, that L, that the action of a functional n on the RL, it is the integral of L squared. Excuse me. Okay. Yeah. So the norm of H is a supremum of L of H, where L is such that this integral is less or equal to 1. This norm can be infinite, and by H capital of gamma, I will denote the space of the subspace of X where this norm is finite. And soon we will see that this is quite an important subspace. Okay, so first of all, it turns out that this subspace H coincides with the space of all integrals of this form. Okay, where F belongs to the closure of the dual space in L2. Okay, so first, to prove this, so first assume that the vector H has the form of the integral of f of x times x. Then we can estimate L of H, which is equal to the integral of f of x times L of x, okay, with respect to gamma. By Cauchy inequality, this is less or equal that the product of norm of f, this is norm in L2, times norm of L, this is also norm in L2, and as I mentioned on the previous slide, the norm of L is norm of L in L2 squared is L of RL. Okay, now if we take the supremum of L of H such that L RL is less or equal to 1, this will be less or equal that norm of F in L2. So we get that the vector H belongs to the Cameron-Martin space. Now, if vector H belongs to the Cameron-Martin space, we can consider the following functional. The functional f capital, it is defined on the dual space as follows. F of L equals to L of H. Okay, so it is a well-defined functional, and sorry. Okay, so and for this functional, we have an estimate that, okay, so since H belongs to the Cameron-Martin space, then we have an estimate that L of H is less than some constant times root of LRL. This implies that the functional is well defined and bounded if we consider the L2 norm on the dual space. Then this means that it can be extended to a continuous linear functional on the on the closure of the dual space in L2. And since this is a Hilbert space, it has a form of the product in L2 with some element from this space. So we deduce that there exists a function f, okay, from the closure of the dual space in L2, such that our functional f capital is equal to the product in L2 of L and F. In other words, L of H coincides with the integral of the product of F times L with respect to measure gamma. So we have that the vector H has the form, okay, so the vector H is the image under covariance operator of some function f. So what we have done, we proved that the covariance operator of measure gamma defines one-to-one correspondence with the space X star gamma and the Cameron-Martin space. Then we can then we can define the structure of the Hilbert space on the Cameron-Martin space as follows. Define the inner product of vectors Rf and Rg simply as the product in L2 of functions f and g. Okay, so in this way we get a Hilbert space H of gamma, okay, which is included into the space X on which the Gaussian measure is defined. Okay, so and now let's define a shift of a probability measure as follows. So if gamma is a probability measure, then H is some vector. So gamma H of A is defined as gamma of A minus H. So this is the shift of the measure gamma by the vector H. And now if we take the vector H from the Cameron-Martin space, then the shift of measure gamma by vector H is equivalent to the measure gamma. And the Radon-Nikodym density of gamma H with respect to gamma is equal to to the following expression. So this is exponent. Okay, so H has a form Rg, yes. So this is actually g of x minus 1/2 norm of H squared. And if we take H not from the Cameron-Martin space, then the shift of measure gamma by H will be singular with respect to measure gamma. Now let's check this. First, consider the case when H belongs to the Cameron-Martin space. And let's compute this integral. Okay, so this is the Fourier transform of gamma applied to the functional L minus Z times G. So now Z is just some real number. Okay, so this is the integral of this exponent minus 1/2. It will be the integral of L of x minus ZG of x squared. Okay, and now if we open the square, the integral of L squared will give us minus 1/2 L of RL. The integral of the product will give us Z times L of RG. And also the integral of Z squared G squared will give us Z squared times the integral of G squared is equal to the norm of H squared. Okay, now and this holds like for all real values Z. Okay, now we know that both parts of the equality, they are analytic functions of Z. So we can apply analytic continuation and replace Z by I. And when we do this, so here we have I times minus Z. Yes. So when we replace Z by I, we will get just 1. Will be exponent. It will be exponent of G, then minus 1/2 H squared. And on the right side, when we take Z equal to I, this cancel, and we get exponent I L of H minus 1/2 L of RL. But this is exactly the Fourier transform of the shift of measure gamma. Yes, because the transform of gamma is exponent minus 1/2 L of RL. And when we shift this measure by h, we get additional summoned IL of h. Okay, so this shows that the shift of measure gamma by h is equivalent to the measure gamma, and this is the form of the radon-Nicodim density. Okay, now next, consider the case when the vector h doesn't belong to the Cameron-Martin space. So this means that the Cameron-Martin norm of vector h, which is a supremum is infinite. Then we can find a linear continuous functional L such that its variance is equal to 1 and its value on h is bigger than any any fixed like integer n. And let's estimate the total variation distance between measure gamma and its shift by h. Okay, so when we take images of measures, then the total variation distance decreases. Okay, so now the image of measure gamma by the functional L, it is actually it is the measure on the real line, and since we take the functional of variance 1, so actually this is the standard Gaussian measure on the real line. Okay, and since L is linear, this measure is a shift of gamma 1 by L of h. Okay. And as we already saw, now these measures are equivalent, and the density of the shifted measure with respect to gamma 1 has the following form. Okay, so the total variation, the distance between these two measures is equal to the integral of the absolute value of so this is 1 is the density of gamma 1 with respect to gamma 1, and this part is the density of the shift of gamma 1 with respect to gamma 1. Further, we can estimate this integral from below by this expression, which follows from the following inequality, that the square of the difference of root of a and root of b is less or equal than absolute value of a minus b. And now we can actually find this integral. So let's do this. So open the square, we will have 1 minus 2 exponent 1/2 t L of h minus 1/4 L of h squared plus exponent t L of h minus 1/2 L of h squared with respect to the standard Gaussian measure. Okay, so 1 integrates to 1. Um, and the integral of the exponent is equal to exponent 1/2 times the coefficient near t squared. So this will give 1/8 of h squared. And the last exponent integrates to 1. So we obtain 2 minus 2 exponent minus 1/8 L of h squared. Now recall that L of h is bigger than n, then this quantity is bigger than 2 minus 2 exponent minus 1/8 n squared. Okay, when n converges to infinity, this converges to 2, which means that the total variation distance between the measure gamma and its shift is equal to 2. Okay, but these are probability measures. So the variation between them can be equal to 2 only when they are singular. Okay, so it means that they are concentrated on disjoint sets. Okay, so we see that the Cameron-Martin space of a Gaussian measure gamma exactly coincides with the space of vectors such that shifts along these vectors are equivalent to the measure gamma. Okay, so the first example, let's consider the n-dimensional space, n-dimensional Euclidean space. So now the Fourier transform of the measure gamma is equal to exponent minus 1/2 a lambda lambda. And now A is the symmetric non-negative definite matrix of size n. And such matrix can be written in the diagonal form. It means that there exists an orthonormal basis in Rn such that so let's write not lambda but vector z. Now lambda I is the eigenvalue and EI is the eigenvector. Now what will be the Cameron-Martin space the norm of vector H, it is the supremum here we will have the action of Z on H, which is the sum HEI VEI, such that so this quantity is less or equal to 1. It is equal to the sum okay, so and we need to understand when this supremum is finite. Okay, so consider the case when we have a zero eigenvalue. Then let's take vector z just to be some constant. Times the eigenvector that corresponds to lambda I. Then for any constant c, this constraint is satisfied because lambda I is equal to 0. Okay, so then this sum will be equal to constant c times h ei. And if h ei is not 0, then this quantity can be made as big as we want. So the supremum will be infinite. This means that if lambda I is equal to 0, then the product of h and ei must also be equal to 0. Okay, so here we can then write the sum when lambda is not 0. And then this supremum will be finite because we can divide by root of lambda I, multiply by root of lambda I, yes, and apply the Cauchy inequality. This supremum will be, in fact, it will be equal it will be equal to the following expression. So this shows that the necessary and sufficient condition for the supremum to be finite is that the components of vector h in the directions of eigenvectors that correspond to 0 eigenvalues of a are equal to 0. In other words, h must belong to the range of a. Let's note that range of a coincides with the range of root of a, and why it is important I will show in a minute. So let's consider another example, standard Brownian motion. Okay, so the distribution of the standard Brownian motion is a Gaussian measure on the space of continuous functions. And it turns out that the Cameron-Martin space of this measure coincides with the space of functions of the following form. So we take a function from L2 and integrate it from 0 to some point. So elements of the Cameron-Martin space are continuous functions of the following form. Okay, where f is from L2. And now know that not of course not all continuous functions have this form. So h, in particular, h is absolutely continuous, and the derivative of h is square integrable. Okay, so how to check this? Let's consider some functional on the space of continuous functions. Now, this functional is defined by some signed measure lambda, and the square of the norm of this functional in L2 is the double integral of minimum of t and s with respect to lambda. Now, we can write the minimum as the integral from 0 to minimum of t and s with respect to r. And when we change the order of the integrals, the integral of this indicator will be the measure lambda of the segment from r to 1, and this will be the same number. Okay, so now this shows that if we consider the mapping that sends a functional lambda into the following function, then actually this is an isometry. Moreover, the range of this isometry is dense. Indeed, let's consider some continuously differentiable function and such measure lambda. So this measure has is defined by a density which is equal to the derivative of g, and has an atom at 1. And if we now compute the measure lambda of the segment from r to 1, this will be minus integral from r to 1 of the derivative of g, which will give minus g1 plus g of r, and plus g1, so we will get g of r. This means that the range of this mapping phi contains continuously differentiable functions and is dense. So we can now extend the mapping phi to the closure of the dual space in gamma. And this extension will be the isometry between this closure and L2. Also, we saw that the covariance operator is the isometry between the closure of the dual space and the Cameron-Martin space. And now let's define the mapping G as a composition of the covariance operator and the inverse of phi. Then G acts from L2 into the space of continuous functions, and actually G of L2. Okay, so this is the image of our disclosure, which is the Cameron-Martin space. So now we just need to understand what are elements of this image. Okay, so let's take some function f. H will be phi of f. And let's check how a linear continuous functional lambda acts on G of H. So this is the same as lambda of Rf, which is the inner product of function f and functional lambda. Okay, and since phi is the isometry, this is the same as the product of h and phi of lambda in L2. This is the integral of hr times measure lambda of the integral from R to 1. Now, this measure lambda of the segment is equal to the following integral, and when we change the order of integration, we get the integral of lambda, the integral with respect to lambda of the function integral from 0 to t h of r dr. Let's compare these two expressions, and we deduce that actually G of h is the integral from 0 to t of h of r dr. So this is exactly the form of the element of the Cameron-Martin space for the distribution of the Brownian motion. And we had one more example. Okay, we had an example of a Gaussian measure in the space L2, which was the distribution of this sum. So I leave this as an exercise to prove that the Cameron-Martin space of gamma, actually it is the image of the root of the covariance operator. Recall that when we had n-dimensional space, then we showed that the Cameron-Martin space coincides with the range of the covariance operator. But in finite dimensional case, the range of A is the same as the range of the root of A. In the infinite dimensional case, we don't have this equality, and in fact, the answer is that the Cameron-Martin space is the range of the root of the covariance operator. Okay, so I think that my time is over. What we will do on the next lecture, we will define Hermite polynomials and eta Wiener expansion for the Gaussian measure, and maybe we will discuss the capacities. So I think that's all for now.
Okay, thank you. Maybe some of participants have questions or comments. Okay, if not, then we will have a break for 15 minutes and then we continue with lecture by Katerina. So thank you. Meet you in 15 minutes.